Biology, and this is the paper solution of December 2017. This is for degree section, semester 3, second year, Mechanical and Automobile Engineering. So here I have divided this video into two parts, and this video will be covering from question number 1 to question number 4. As such, here I have not solved it completely, but I have given short answers, okay, or few points where you can elaborate the points or add your extra points. Okay, here it is only short answers to just give you the idea of the answer, but this is not the complete answer. For all the questions, I have also written the marks for which each question has been asked for. So let us start. Difference between steels and cast iron. So here I have written 2 points, but as such it is for 5 marks, so you have to write 5 points. So steel as such, it is having low carbon content, and cast iron, it is having high carbon content. Steels are less brittle, cast iron are more brittle. Question number 1B, that is the allotropic modification of iron, that is for 5 marks. Here iron is allotropic metal, so which means that it exists in more than one type of lattice, that is structure, that is BCC, that is body centric, FCC, that is face centric, depending upon the temperature. In normal temperature or the normal room temperature, iron is BCC, it is body centric in lattice arrangement, whereas at 910 degrees centigrade or Celsius it changes to FCC, that is face centric, and then at 1400 degrees Celsius it comes back to BCC again. The same thing has been represented in this diagram, that is BCC, okay, up to 910 degrees Celsius, and then it becomes face centric, and then again at 1400 degrees Celsius it becomes BCC. So BCC up to 910, then it becomes FCC, then after 1400 degrees Celsius, then again BCC. And it is shown that it is like alpha, okay, up to 910, and then after 910 it is delta. Okay, so this has been represented in this diagram. Okay, so you have to elaborate each point and also explain the diagram in detail. Here I have given you just the small explanation about the question. Then the classification of the material. So materials are of 3 types: metals, non-metals, and material combinations. Metals, it can be ferrous metal or non-ferrous metal. Non-metal, it can be ceramic or organic polymers. Materials combination, it can be composite like visco reinforced plastic, metal reinforced metal, metal ceramic, carbon reinforced rubber, ceramic polymer, or polymer cement concrete. Or it can be alloy, it can be ferrous alloy or non-ferrous alloy. So this was classification of material. Then question number 1D, that is mode of deformation in the material. So deformation is defined as the change of the shape of the body caused by the application of the force. So there can be 2 types of deformation. One is elastic deformation, one is plastic deformation. Elastic deformation is the deformation which appears with the application of stress and which disappears when the stress is removed. Plastic deformation, it is the permanent deformation which remains in the metal even after the removal of the stress. So you have to elaborate it more because it is for 5 marks. Then question number 1E, it is stainless steel and its classification. So first you have to define and explain stainless steel. So here I have written 1 line about stainless steel, that is the greatest advantage of stainless steel over the plain carbon steel and alloy steel is that it provides high resistance to corrosion in most of the environment and media. When we talk about classification of stainless steel, it can be ferrite SS, that is ferrite stainless steel, where the chromium content is from 12% to 27% and carbon content is 0.08% to 0.2%, and it contains structure that is ferrite phase, martensitic stainless steel. It is having chromium 12 to 18%, carbon 0.1 to 1.2%. It contains hard martensitic phase after hardening, austenitic stainless steel, where chromium is 16 to 24%, carbon is less than 0.2%, and nickel is 8 to 22%. So it is having the structure that is austenite. Then question number 2A, which talks about define critical cooling rate, describe various cooling curves on TT diagram for eutectoid steel and discuss the transformation. This is for 10 marks. So what I have done here, I have defined critical cooling rate, which is defined as the lowest cooling rate which produces 100% martensite with minimum internal stresses and deformation. So critical cooling rate, that is CCR, is defined as the lowest cooling rate which produces 100% martensite with minimum internal stress and distortion. So here, as you can see the curve, on the x-axis it is time in seconds and on the y-axis it is temperature. Depending on the rate of cooling, different type of grain structure can be formed. As you can see, when we talk about this curve, which you can see here, which is having a nose, it is the main part of the figure, and then depending on the different rate of cooling, you have annealing, as you can see, number 1 and 2. So when at this particular temperature or the rate it is cooled, then we have the perlite, which is coarse perlite and fine perlite, and then we have this normalizing, and then the curve number 4, which is missing the nose and going to the right side of the nose, and then the curve number 5, which is the CCR, that is critical cooling rate. So then 100% martensite can be formed, and then curve number 6, as you can see over here, and then 7, which is also having a temperature, which is held for some time, and then again it is cooled further. So it is austempering, it is called as. So as you can see here, different processes have been shown: annealing, normalizing, and then austempering. And at various temperature or cooling rate, perlite and bainite can be formed, and at certain particular cooling rate you can have coarse perlite, in these temperature ranges, fine perlite, upper bainite and lower bainite. And as you can see over here, we have capital A, which is austenite, and here, as you can see, that is martensite, and in between you can see A plus M, that is austenite plus martensite. Here you can see MF, and here you can see MS. So here also you can see on the left side PS, and here PF, that belongs to perlite, and this is BS and BF, which belongs to bainite, and in between, as you can see, perlite, and this is A capital, that is austenite. So here in between, as you can see, it is A plus P, and here you can see A plus B. So this is the critical cooling rate, that is CCR, and this diagram is called as continuous cooling transformation diagram.